In this video, I'm going to cover simplifying radicals and then some operations with radicals. Radical is just another term for square root. First thing we need to think about is what a perfect square is, and that would be any number whose square roots are rational, okay? In other words, no decimals. So if you think about any number squared, that number is a perfect squared. So like 2 squared would be 4. Oh, there we go. 3 squared is 9. 4 squared, 16, 25, etc. So we'll just make a list here of the common ones that we should already know. 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, and 15 squared. Usually you'll be dealing with numbers on that in the lower end of that, but it is useful to know at least up to 15 squared. Okay, so when we simplify, we need to ask ourselves 2 questions. The first question is, what perfect square divides this radicand? And radicand, if you haven't heard it before, this is a term that means the number that is under the radical or under the square root symbol. Okay, so we ask what perfect square divides our radicand, and then we ask how many times. And we're going to factor, okay, remember factoring is splitting into pieces that are multiplied together. So we're going to factor our radicand into a perfect square, and then whatever is left over, its other number. Okay, so looking at 16, well 16 is already a perfect square. Square root of 16, that's just 4. I did put this one in here though because sometimes with simplifying radicals, we think of it the same way we do reducing fractions, and we think, oh yeah, just keep reducing as far as you can. That's not the case with simplifying radicals. Once we have applied the square root, once we've used that operation, it's no longer there. So what I mean by that is I don't want anyone to get confused and think, okay, well the square root of 16 is 4, and then the square root of 4 is 2, so that means the answer is 2, okay? That's wrong. That's wrong. Once we have taken the square root, that number is gone. 1 second, everything just shifted. There we go. All right, let's try that again. So the square root of 16 is just 4. The square root symbol is an operation just like a plus sign or a minus sign or a division sign. If you were to have 5 plus 2, you wouldn't write 7 plus because the plus has already been used. Same thing here. Once we've used that square root, it's no longer written, and the 4 is all that's left. Okay, then looking at root 12 now. So we ask what perfect square divides this radicand, and 12 is divisible by 4, which is a number on our list. So we factor this into the square root of 4 times, and then how many times does 4 go into 12? 3 times. Now if you notice, both of those still have radicals on them. We have not used the square root yet. All we have done is separate the 12 into 4 times 3. Both of those still have radicals. Now, can we apply the radical on the square root of 4? Yes, we can. The square root of 4 is equal to 2. So we replace that with a 2, does not have a radical on it anymore, okay? And then the square root of 3, can we take the square root of 3? No, we can't. So the radical stays because it's an operation that we can't use, and our answer is 2 root 3, okay? I don't want you to think, okay, there's a 4 and a 3, and I know there's a 2 in there, so is it 2 root 3 or 3 root 2, and just kind of guess which one goes on the inside and which one goes on the outside. If you understand the process, if you understand that we are looking for a perfect square and then applying that radical, okay, we're applying this radical right here because it can be applied, all right, then that will help you know what your final answer is, and you won't kind of just guess and check which one goes on the outside. Okay, 3 root 75. If we have a number on the outside, the operation that's inside here is multiplication, so that's 3 times the square root of 75. That 3 is not going to affect anything with the simplifying. We will just need to multiply the 3 times whatever other whole number is on the outside of the radical. Okay, so looking at the 75, we ask what perfect square divides that? And we can see 75 is 25 times 3. Okay, it goes in 3 times. So we can write that as 3, that 3 stays there, and then it's root 25 times root 3. Okay, and again, that first 3 is just kind of hanging along for the ride here. All right, so we've got a 3, and then the square root of 25 is 5, so we're applying that radical. The root 3, we cannot apply a radical to that, so it stays root 3. And lastly, we do need to multiply the 3 and 5. That's not addition, it's multiplication, so it's not 8. It's going to be 15 root 3 for the final answer. Okay, and by the way, if you're just getting the hang of simplifying radicals and you want to be checking to see if you did them correctly, one way that you could do this is you could plug your final answer, in this case the 15 root 3, into a calculator and look at that decimal, and the original value, 3 root 75, into a calculator and see if you get the same decimal. We don't want decimal answers, but that's one way that you can check to see if your simplified answer is the same as the original. Now, that's not completely foolproof, because sometimes a value can be simplified more than once, like in this next example. So even if your answers are the same, your values are the same, you may not have simplified it completely, but it is going to be a little bit useful if you're trying to check. Okay, root 72. Like I said, sometimes you have more than one way to simplify this. If we're looking at 72 and we're looking for perfect squares that divide that, we actually have a few of them. 4 goes in, 9 goes in, and 36 goes in to 72. Okay? If there's more than one, we want to pick the biggest one, because that minimizes the number of times we have to simplify. And since that's 36, we're going to write this as root 36. And then how many times does 36 go in? It goes in twice. So it's root 36 times root 2. Okay? And then the square root of 36 is 6. Square root of 2 we can't take, so that radical stays on there, and our answer is 6 root 2. Now, let's say that we didn't recognize the 36 first. Maybe the first thing we recognized was a 9. We know that 9 goes in 8 times. So instead of this, I'm going to write it up here, instead of the 36 and 2, we separate it as root 9 times root 8. And then the square root of 9 is 3. Well, that's fine, except the square root of 8 can be simplified again, because that's 4 times 2. Okay, and then the square root of 4 is 2, so 3 times 2, we'd be right back at 6 root 2. So we could still get to our right answer, but it would take us 2 simplifying steps instead of 1 if we don't find the biggest perfect square. So if you have a number that's a little bit bigger and has more than one perfect square that divides it, use the bigger one. If you don't recognize it right off the bat, that's not a problem. Just check your radicand that's left at the end and see if that still has any more perfect squares in it. And if it does, continue simplifying. Okay, this next one a little bit different because we've got a variable in there. We're still going to simplify the root 98 just like we did the other ones. So let's do that, the numeric part first. Looking at our list, we want to know what perfect square goes into 98. And 98 is 49 times 2. So I want to write this as root 49 times root 2. Okay? And now let's look at the x's. Well, x to the 5th means x times x times x times x times x. There's 5 x's that are being multiplied. We know that. And we are looking for something where we can take the square root. I cannot take the square root of x to the 5th. There's x to a whole number power times itself does not equal x to the 5th. However, x to the 4th we can take the square root of. So I'm still going to separate x to the 5th into a perfect square and the rest of its factor pairs. So I'm going to write that as the square root of x to the 4th. And then there's 1x left over. Okay, you can put a 1 on here if you want, but you don't have to. So now we've got square root of 49, which is 7, and I'm going to leave a little space here for the variable. The 2 stays on the inside. And then the square root of x to the 4th, well, this is x squared squared, x squared times itself, so that means the square root of x to the 4th is x squared, and then we have one more x left on the inside. So our answer here is 7x squared and then root 2x. All right, now some of you may be thinking, when you learn to write terms that had numeric parts, coefficients, and they had variables, we always put the variables at the end. So the question may be, why don't we put the x squared after the root 2? And the reason there is that if there's anything that's not under the radical, you really want to put that in front. Okay, that's really the proper way to write it, because sometimes we're not very clear on where the end of this is, where the end of our radical is. So if we wrote, root 2x squared, it might be a little unclear whether the x squared was supposed to be under the radical or whether it was supposed to stop before the radical, just because maybe we don't write that as nicely as we should. So to avoid that, we put anything that's not under the radical in front of the radical, even if it's a variable. And it's okay if you have variables both inside and outside. Okay? All right, so that's simplifying radicals. Moving on to some operations with radicals, we're looking at adding and subtracting first. In order to add or subtract, we must have the same radicand. Now, sometimes two numbers don't have the same radicand, but maybe one or both of them can be simplified, and then you end up with the same radicand. So we do want to say, okay, well, is it possible to simplify first? So looking at this first example, I see a root 20, a root 45, and a root 5. Well, none of those match, but I know that the 20 and the 45, I could simplify both of those, okay? So root 20, using what we did before, I know that's 4 times 5. Okay, so that gives me 2 root 5. Root 20 is 2 root 5, okay, plus, and then root 45 is going to be 9 times 5, so 3, and then root 9, root 5, so 3 times 3, 9. Root 5, I didn't just take that radical off. I multiplied the square root of 9, which is 3 times the 3 that was already there, and then minus root 5. Okay, now all of the radicands match, so I can add and subtract. And the rule for adding and subtracting, once we have matching radicands, is that the radicand stays the same, and the number that is outside the radical gets added or subtracted, okay? Kind of like with a fraction, the denominators stay the same and you add and subtract the numerators, okay? Because this is saying how many root 5s do we have? We've got 2 of them. How many root 5s are here? There's 9 of them for a total of 11 root 5s, okay? And then we're taking how many of them away, and since there's no number in there, it's kind of like an understood 1. So we've got 11 root 5s. We're taking away 1 of those root 5s, and we are left with 10 root 5s, okay? So when adding or subtracting, the radicands do not change, only the number that is in front. Okay, moving on to this next one. Again, we see that none of the radicands match yet, but we do want to try and simplify. 28 is root 4 times root 7, so that's negative 2 root 7, okay? Root 14, I can't do anything with that, so I'm going to leave it, 11 root 14, okay? And then 63, let me fill in this middle part so my statements are complete. Okay, 63 is 9 times 7, okay? So this is 3, I'm going to multiply that times the 6 right there, so 18, doing 2 steps at once there, 18 root 7. Okay, now looking at these 3 terms, 2 of them have a root 7 in their radicand, so I can combine those 2. However, I cannot combine it with the 11 root 14 that's here, okay? If we have terms that don't have matching radicands, or maybe one of them is a whole number, that's no problem. That just means we have more than one term in our answer. Okay, so looking at the ones we can combine, we have a negative 2 root 7. We're subtracting 18 root 7s, so that's a total of negative 20 root 7 plus 11 root 14. And again, I can't combine those. There's no way to force that 7 and 14 to match, so I just have 2 terms in my answer, and that's it. And as far as the order, it doesn't really matter what order you write them in. Okay, multiplying and dividing. When we are multiplying and dividing values that have radicals or expressions that have radicals, we have to combine the parts that are in the same place. So the outside values get multiplied together and the inside values get multiplied together. But you're never going to multiply something outside a radical times something inside a radical. So if we had, for example, 3 times root 5, there's nothing we can do with that other than just writing 3 root 5. Okay? We can't write, it's not root 15, and it's not 15, or It's not 15, okay? It can't be any of those. It just stays 3 root 5, okay? And as always, we do want to look for places where we can simplify. Okay, so looking at this first example, I have 8 root 10 times root 6. Again, if there's nothing written here, that's just kind of an understood 1. So the outside parts, 8 times 1, that's just 8. The inside, root 10 times root 6, is going to be root 60. And now we ask, is it possible to simplify? Yes, it is. 60 has a perfect square in it. Okay, 60 is 4 times 15. Square root of 4 is 2. I'm going to multiply that times the 8. So 16 root 15 is my answer. Okay, and again, I don't think I said it before. At any time you want to pause and try on your own, you are more than welcome to do so. Okay, for this next one, I'm going to apply the distributive property as well. So the negative 2 root 15 is going to be multiplied by both of these inside terms. Okay, so starting with the first one, negative 2 root 15 times negative 4 root 3. We multiply the outside pieces together. We get 8. Inside pieces, 15 times 3 is 45. Okay, and then multiplying the negative 2 root 15 times 5 root 5 gives us negative 10 root 75. All right, and now I simplify where possible. 45 is 9 times 5, so this is 8 root 9 times root 5. So that's 3 times the 8 is going to be 24 root 5, okay? And then 75, we just did this one up above in one of the previous, did we do this previous example? Maybe we didn't. Okay. Root 75 is 25 times 3. Okay, and square root of 25 is 5. Multiplying that times that 10 is, negative 50 root 3. And because these radicands do not match, I cannot do any more, so that's my answer. Okay, now when we divide, we need to what's called rationalize the answer, okay? In other words, that means we do not want any radicals in the denominator. No radicals in the denominator. Now, we can't change the value of our expression, but what we can do is we can change the way that it's written, okay? And if you think about adding and subtracting fractions where you had to get a common denominator, remember we would multiply one of the fractions by something over itself, like 3 over 3 or 6 over 6 to get a common denominator. We're going to kind of use that same process where we multiply by something over itself and we pick a value that will give us a whole number in our denominator. So I'm looking at this root 3, and I know that if I multiply it by another root 3, root 3 times root 3 is 3. They don't cancel out. Root 3 times root 3 is 3. And then the 5 times 3, I get a 15 in my denominator, and that's now a whole number. So root 3 is what I'm going to multiply my denominator by. Now, to not change the value, I do need to multiply the numerator by root 3 as well. Okay, so I now have 2 times root 3 in the numerator, which is just 2 root 3. And then 5 times, we know those have a product of 3, so 15 in our denominator. We do check, is there anything that can be reduced? No, there is not. We cannot reduce a root 3 and a 15 because the 15 is not under the radical. So that's it. 2 root 3 over 15 is all we can do there. Okay, another dividing example. Root 20 and root 45 are both under the radical. We don't want a radical in our denominator, so we're going to need to rationalize, okay? Which means if we follow what we did last time, we can multiply by root 45 in the numerator and denominator, okay? However, there's something that's going to make our lives a little bit easier. I'm looking at this, and I see that 20 and 45, which are both under a radical, are both divisible by 5. And because our rule for multiplying and dividing, okay, remember up here we said both inside or both outside the radical can be combined. And that's not just multiplying, that's dividing too. So because the 20 and the 45 are both under the radical, I can go ahead and divide that, or in other words, reduce that just like any other fraction. So I'm going to make this a 4 and make this a 9. Well, now, 2 times square root of 4, that's 2 times 2. Okay, so that's just a 4, and the square root of 9 is a 3, and now I'm done, and I did not have to go through the rationalizing process because I recognized that the 20 and 45 could be reduced first. If we had done it the other way where we didn't recognize that, let me rewrite this here. Okay, we would multiply by root 45 over itself. Okay, and then we'd have 2, and then 20 times root 45. Oh, I need my 2. So we would have 2, and 2 times 45 is 90 with another 0. So 2 root 900 over 45. And the square root of 900, if you recognize right off the bat that's 30, that's fine. Otherwise, you could break it into 9 and 100, or however you want to do that. But we do get 2 times 30, which is 60 over 45. And then we notice those are both divisible by 15. 15 goes into 60 4 times. It goes into 45 3 times. So we still get to 4 over 3, but you notice that took a lot more work than just reducing first. Okay? So if possible, look for things that reduce first. Okay, for this next one, again, I'm looking and I recognize that the 21 and the 14 are both under a radical and they are both divisible by 7. So I'm going to reduce those by 7. So this is going to be a root 3 and this is going to be a root 2. Now, can I reduce the 3 and the 6? And the answer is no, because remember the 3 is still under this radical and I can't combine a number that is inside with one that is outside. Okay. At this point, I do need to rationalize because I still have a square root of 2 in my denominator. So I'm going to multiply by root 2 over itself. Okay, so my numerator, root 3 times root 2, is now root 6. And my denominator, I have 6 times, that's now 2, whole number 2. 6 times 2 does give me 12. Okay, and 6 and 12 could be reduced, but that's not a 6, that's a root 6. So I cannot reduce any further. So root 6 over 12 is my answer. Okay. Last one here, again, rationalizing one more time. I need the root 7 out of the denominator, so I multiply by root 7 over itself. 4 root 3 times root 7 is going to be 4 root 21. And 5 times, this has a product of 7. Remember, they don't cancel out. They have a product that's a whole number. So 5 times 7 gives me 35, okay? And I double check, can I reduce? No, because 21 and 35, while they both share 7, 21's under a radical. Sometimes you will have where these two numbers can be reduced. If that's the case, definitely reduce them, but in this case, they can't. So 4 root 21 over 35 is our final answer.